So then what happens is that, ideally, they go with some helicopters here, and they basically, they deploy some drifters in the water. These drifters move, and as they move, this data is assimilated into the model so that you're going to have a surrogate model that is more accurate in this region and at this time. Okay? So in general, what happens is that you have model in the future, in the past, but the most accurate data is the data that is happening now in that region because it's augmented with local observation. For instance, they say, oh, let me actually assimilate temperature information, drifter trajectory, etc. Okay, so that's the challenge, and this is basically similar challenges when oil spill happens. And well, especially in the Mediterranean recently, in the last few years, thousands of people died for crossing the Mediterranean. As there was a refugee crisis. Okay, so basically these properties or constraints for this particular application suggest that Lagrangian methods are not really ideal because those require integration of trajectories, and we saw that basically future and past data are not, ideal. They are not as accurate, okay? And eventually you want to start providing information to the Ghost Card where to go immediately, as soon as possible, because 6 hours is very small time interval. Okay, so what is basically the standard approach of search and rescue is that, let's have a little bit of notation. So fluid particles, they will obey this differential equation, x dot equal to v of x at t, that's the velocity of the fluid. Floating objects, usually you can write them in this form. All the equations that Anupam was discussing, you can cast them in this form where epsilon is a small parameter. Anupam was calling it capital V yesterday, is the speed of active motility divided by the speed of the flow. Okay, so then you can say, okay, this is the ocean model velocity. These are a lot of things that you don't know typically. This could be, I don't know, the current windage in that particular region in that particular time. I don't know, the inertia of the objects, the shape. There is basically so there are lee waves or currents on the surface of the ocean that will also affect the transport on top of the advection from the water. But those are basically typically unknown. Okay, you cannot really start resolving that and doing Monte Carlo simulation because you really have to react very quickly. So what they do, the current approach is you do that, then they run ensembles of all these possible uncertain parameters. They do Monte Carlo. Monte Carlo provides you a probability map of where things would accumulate most likely, and then on top of this probability map, you're gonna start having basically scanning of, for helicopter or boats, you have to scan regions of high probability map, okay? And then you say you go there, you didn't find it, update the probability map with a Bayesian inference. And what happens basically is that if you are doing a search with Bayesian updates, and in a simple setting, usually you would expect that this probability map becomes more peaked over time. Eventually, it's okay. I'm gonna go very, I'm gonna increase I'm gonna decrease the uncertainty of where the objects could be, in general. However, in the classical example of search and rescue, this is not the case because you have the ocean, which is a very chaotic system that is forcing the search. So you start updating this probability, and it becomes even more diffused. So it's a very challenging thing because it's okay. Where do I go? So there are a few problems. This is very slow. Okay, it doesn't really necessarily converge because the ocean surface is forcing this system. So therefore, it's not like you're looking for a fixed source in a very steady environment. So the more information I accumulate, the more sure I am where the source will be after I accumulate information. This is not the case because it's very time dependent. And the other thing is that once you have this probability map, you are left with a two-dimensional probability map, and then you have to do a further scanning. You have to do some pattern scanning within this probability map to see where to go, to scan this area. So this is basically a little bit of structurally, not favorable to have this procedure. So then we said, okay, can we actually identify or define the notion of short time attractors and see which are very quick to compute because short times Eulerian coherent structures, so Eulerian you don't even have to integrate trajectories, and these are so-called in the terminology in the language they are codimension 1 structures, the ridge of the FTLE or stuff like that. The codimension 1 means basically they are 1 dimension less than the dimension of the phase space of the velocity. 2-dimensional flows, codimension 1 structure are lines. Okay, 1-dimensional lines or curves. In 3D, they are surfaces. So this is beautiful because basically now you don't have to search volumes or areas, you go with lines. So you have a technique that already returns you something that is very prone to be explored because it's easier to explore a line rather than an area. Okay, it's okay. Can we do that? Okay, so the hope here is the following. So the hope is that, okay, we cannot really resolve this uncertainty because, if you really know detailed information of G, I can construct traps or transient attracting profiles. These are also called Eulerian attracting coherent structures. We call it traps for this specific application. This is transient attracting profiles. The idea is that you have velocity available. If you give me information about G, I can also modify the definition of traps and say, okay, if you're looking for inertial particles, I'll tell you where they come. Or if you're looking for particles of this particular shape, I'm just going to consider this as the new velocity field and define the traps on that. But the problem is that you don't really know G. So the question we ask is, can I extract the most robust information of the velocity field that will likely have an impact also on the trajectory of floating objects over a very short time? Okay? Because basically epsilon is small. Okay? So there's a very important distinction here. So Anupam showed you, Anupam equations were very similar to this. In general, also the equations for phytoplankton, for everything is of this form. It's a velocity field of the fluid plus a small parameter times some other functions. So this is always small. Now, if you're interested in the long-term behavior of things, this small parameter can make a difference. But over a very short time, it doesn't. Because, this is going to be velocity plus a small correction. Okay, so it's very important to understand Lagrangian versus Eulerian versus asymptotic. Okay? Okay, so what we want to do is this. So basically, things fall in particular region, and because the initial condition is uncertain, so basically you're never going to know where you land in this unknown domain, we said, I'm not going to insist on trying to resolve the uncertainty to initial condition because it's a lost game. On the other hand, what we want to do, we want to say, where are the most attracting regions over a very short time in this dynamical system, right? So basically, pictorially, this is what we think. So we think this is an uncertain location. Now I want to understand, so this would be a short-time repeller, and then eventually there is going to be a short-time attractor, okay? And you can actually have maps of these structures in the ocean as they evolve, okay? So there is this model velocity field. These are instantaneously to compute. We are going to see how we are going to compute it. And then, to be honest, I don't really care about predicting all this trajectory. I just want to understand where are the most attracting region. It's like the way I think about it is more, imagine that you have a metal table, and there are some hidden magnets below that someone can move, and they throw a coin. Predicting the trajectory of the coin is going to be very hard because you see this magnet, the dynamics is very transient on the ocean surface, etc. But if I have the stronger magnet, most likely I'm going to get rich with the coin. Right? I'm going to get the coin, right? So this is a little bit of an intuition of forget about reconstructing the full trajectories, focus on where are the most attracting regions in this system over a very short time. Very short time in this case means that you can compute them with a single snapshot of the velocity field. One snapshot, compute where are the Eulerian attractors or traps, and then when there is the new batch of velocity available, you recompute it and you see where it evolved. Okay? Okay, so basically this is the problem. So you can think of this as there is a set of possible initial conditions, which is like this. and now, they will always go to usually in different locations, but eventually I want to identify the attractors or the short-term attractors that will most likely attract whatever is floating, regardless of the specific trajectory of each one of them, because I don't know which trajectory is going to be the relevant one. Okay. And this is what I already told you. Can we actually build traps based on fluid velocities such that they will attract floating objects? Okay, so how do we define these traps? Okay, so basically this is a little bit of the slides that I used at the beginning. So, we basically passed from asymptotic attractors in the book. This is basically you anchor yourself to a fixed point, you do this construction with center manifold theory, you can compute unstable manifold, they only work for steady velocity fields, so this would be impossible. And also, if you wait for infinite time, there's no point of doing search and rescue. So the question is, okay, then there was basically the finite time setting, or the Lagrangian coherent structure. Here we are bringing this limit to the opposite. What happens over a very short time? Okay, and an interesting thing that you're going to see is that even in this case, if you just look at the streamlines of the velocity, you don't get the right answer. Okay, we're going to see why. So that's what we want to do. Now we want to identify where are these objects, these curves, red curves, let's say the attractors, the short-time attractors that will actually attract nearby particles or floating objects over a very short time, infinitesimally short time. Okay, so this is basically the other day at the course. We have basically a velocity field, the flow map, just the final position of a particle. Then you have the Cauchy-Green strain tensor. And remember, what really does the Cauchy-Green strain tensor? Just encodes all the Lagrangian deformation of of any particular material fiber, zeta 0. Okay. Now let's use what we learned the other day. So now we are saying, so remember, Cauchy-Green is something like, so Cauchy-Green is df transpose times df. Okay, so this encodes all the possible Lagrangian deformation that you start at any point you start, initial fluid configuration. This is, you're imagining a ball of initial conditions here, and for any one of the points on this ball, Cauchy-Green tells you how it's going to deform. Okay, so now this of course is Lagrangian and requires a time interval t0 t. What happens if I want to understand so T0 T, or eventually you can write this as T0 to T0 plus capital T. What happens if I now want to understand in the limit of T going to 0? What happens in this case? Okay. Well, what do you usually do when you want to understand? You have a function of time, and now you want to understand a limit for T going to 0. Taylor expansion. Okay, so let's do it. So basically you're going to get a C at T0 plus, let's say, T of x0. Well, yeah, basically, let's do this. I don't want to repeat this, but okay, what's going to happen? So the first one is evaluating the point at T equal to 0. Okay, what is it? The Cauchy-Green at T equal to 0? T equal to T0. This is basically, now this is going to be the leading order term, which is when T is equal to T0, which means basically T equal to 0. How is that transforming? Okay, df T0 T0, what is it? What was the initial condition of the equation of variation? Identity. So f, remember f is equal to x0 plus the integral of the velocity along trajectory, okay, from t0 to t. You have to call this tau, it doesn't matter. This is t0 to tau, right? So basically, the position at t equal to t0 is going to be equal to the initial position. Therefore, when you take this, when you eat this with a gradient, you're going to get, this is going to be the gradient of x0 with respect to x0 plus the gradient of this guy. This you can basically remove because basically this is a t equal to t0, t equal to t0, so basically this is telling you that the derivative of x0 of f t0 t0 is equal to identity. Okay? Okay, so what is this? This is basically identity transpose times identity is identity. Okay, plus, now we need the derivative of Cauchy-Green with respect to time. So we basically need the time derivative of Cauchy-Green with respect to time evaluated at t equal to t0 times delta t plus order delta t squared. Right? So, fine. What is this? What is this now? It's c dot. Okay. So let's do c dot. This is the total derivative. Where this means total derivative. Okay. So then we have to do c dot is equal to what? We just expand the product. So it's going to be now df trans dot times df plus df transpose times df dot. They are all total derivatives, right? Okay, what is now df dot? The most beautiful equation we wrote the other day, that's the equation of variation. Remember? So df dot is equal to the gradient of the velocity field, we call it v here. So this is going to be the gradient, the Eulerian gradient of the velocity field v along trajectory, so t0, t, x0, t, times the deformation gradient. Remember, this is what we did the other day. Okay, so now let's plug it in here. So now I use these two together, and I get here that c dot is equal, is going to be equal to df transpose. So this is going to be df transpose times dv transpose. I just transpose this guy times df. So this is basically df transpose. I'm going to get the transpose of this times df plus this guy is going to get df transpose times df dot, which is again the same, dxv times df. Right? Okay, but now we have to evaluate this guy at the initial, at t equal to t0. Okay, when you evaluate that at t equal to t0, what do we get? Okay, let's evaluate all of them at t equal to t0. df at t equal to t0 equal to identity. Cool, so this is gone, so this goes to 1, this goes to 1, this goes to 1, this goes to 1. So c dot at t equal to t0 is equal to dx v. Of course, when you evaluate f at t equal to t0 is at x0. So this holds at any point. I mean, you can call them the way you want. You can call them x0 or x comma t plus dxv x comma t. Okay, and what is that? It's twice the rate of strain. Yeah. So basically, we learned that, which is not surprising though, right? So what is governing stretching over a finite time is Cauchy-Green, and the infinitesimally short time is the rate of strain. So basically, we learned that basically c t0 t of x0 is equal t0 plus t in this limit of t going to t0, for t going to 0, is equal to identity plus twice the rate of strain tensor. I want to call the rate of strain tensor S, xt. I mean, I can just call this x0 t0 delta t plus order delta t squared. Okay, so basically, of course, there is going to be, at the initial condition, nothing is deformed, so we're going to start with your initial fiber x0 plus a little order correction, first order correction that is going to be set by the rate of strain tensor. Okay, so now if we want to understand attraction or repulsion, actually attraction and repulsion rates, you have to play with S and not C. That's the leading order correction is all included in the rate of strain tensor. Is this relatively clear? You can redo the derivation independently, but it's basically that's what you get. So when you differentiate C with respect to time and evaluate it at t equal to t0, and you get that this is basically the leading order correction, and that's the rate of strain tensor. And therefore, now basically there are two objective tensor fields. For any initial condition, initial configuration, you can say, okay, if I start at x0 and I want to understand what happens over, I don't know, a week, you compute the Cauchy green that you already did in your computer. Or if you say, okay, I really want to understand what happens in a very short time from this time, then it's all the information are in the rate of strain tensor. And these two tensors are both frame independent. They are objective. They check all the right requirements, basically, to identify material deformations of a continuum. In this case, is basically fluids. Okay, fine? Okay. Okay. So now we want to understand, okay, now we have the same problem we had before. We have a tensor. It's a little harder to visualize this tensor. What do we do? Okay, so let's try to... So this is what we did at with George. This was basically my first paper of the PhD. We said, let's try to identify what are the most attracting curves in a dynamical system over a very short time. So to do that, you basically parameterize. So you're in 2D, this case. Now you parameterize a curve. Think about this is the ocean, and now parameterize a curve x of s. This is a vector. X of s is a vector, so you're going to have x1 of s, x2 of s, which is equal to x of s. I don't want to write this, but it's implicit that this is a vector. S is just some parameterization, could be arc length or whatever you want. It doesn't have to be even arc length. So the more you scan s from 0 to sigma, which is the length of the curve, and this is going to trace a curve in 2D, right? So this is going to be x of s1, x of s2, x of s3. So this is your curve, gamma. Okay? And this curve is going to have a normal, so a tangent vector, which is dx ds, which I'm going to call it x prime. And then I can also define a normal, which is x prime rotated by 90 degrees, n of s. So now I have this curve. I don't know where these curves are. Eventually, I want to go chase these curves that are the most attracting in my dynamical system phase space, but I have to set up the problem. So I'm going to look for curves, convention 1 structures, that you have to parameterize them. So you have to pick parameterization x of s, and you're going to need tangent direction and a normal direction. So this is basically the parameterization. It's just the mathematics is not important. And then what you want to do, you want to say, okay, now I have this curve, and I know that there is going to be the stretching rates of every neighboring points on these curves will be governed by the rate of strain. That's what governs the material deformation. So what I want to understand now, I want to say, okay, imagine that I have a normal distribution of vectors to these curves, and I want to understand how much do I attract to this curve, because that's basically my notion of short-time attraction. So what I want to do now, I want to say, okay, how much the normal vector to this curve shrinks. That's a measure of pointwise attraction. That's basically this quantity. The normal repulsion rate or attraction rate is the same. You say, okay, I'm going to have r times x prime is the normal at any point. Okay. Then I'm going to say I multiply it by s. This is basically the S times this normal, and then I project it on N, which is R times X prime. I'm just I'm gonna put now the R inside in this quadratic form. So I'm gonna have basically a functional that is gonna tell me how much this normal fiber will stretch or shrink. Okay, is it clear? That's basically exactly. And then I say, okay, this is stretching or shrinking, and I just want to divide by the norm of my parameterization. So if you pick unit parameterization, you can set this to 1. Okay? So this is going to tell you, regardless of where you are in your phase space, so something, let's say this is the ocean, then it's going to be longitude and latitude. And now you're saying, okay, I don't know what these curves are. I'll tell you how to compute these curves, but for any curve, gamma, I'm going to tell you at any point, tell me the normal to this curve, and I want to interrogate, because there is a flow field in the background, and the velocity field, so here. Okay, this velocity field is going to have basically a rate of strain tensor that I know governs stretching rates or deformation rates over a very short time, and then I want to say, okay, this curve, this point, is it going to experience a stretching rate or a contraction rate? Okay, and this quantity is just q prime, q dot, little q dot, okay? This quantity depends on the properties of the flow, S, depends on where you are, point, in your basically dynamics, it depends on where you are, and also where you are, it depends on which fiber do you want to interrogate, which is the normal to the curve. Because we know that, as we've seen from Jeffrey's equation, like we know that if you start changing this direction, you're going to have different shear contribution or different stretching rate contribution. Fine. So basically, that's what happens point-wise. Now I say, okay, let me actually consider an average of this quantity on some curve gamma. That's my functional. It's the average normal repulsion rate or stretching rate, if you will. Basically, it's just 1 over the length of the curve, integration over gamma of this little quantity. Okay, so this is now a functional that depends on, of course it's going to depend on the velocity field, etc., but the velocity field is given to us. So the only thing that is unknown is where is gamma? Where are the curves gamma that, given this velocity, will spot the regions that are the most attracting regions, right? So to do that, so basically now you say, okay, I'm going to define these traps as the minimizers of Q. So those are basically, they are going to be the curves that will maximize the attraction rate, which is the opposite of repulsion rate. Okay. So when you have this problem, it's a calculus of variation problem. You have a functional, and you look for the extremizers of this functional. Okay. Basically, you take the first variation, the variational derivative of this functional with respect to the function, basically gamma, which is you have to parameterize perturbation to this x of s. And you're always going to get a boundary term and an integral term, okay? And then you can solve the integral term, and this is going to give you basically the Euler-Lagrange equation. It's going to be basically a PDE, an OD, for the curve x of s that is going to actually maximize, or at least as a first order, a zero first order variation, so it's basically an extremizers of this problem. Okay, so basically this is the philosophy. And this is going back to the lecture number 1. Here the coherent structure really depends on what you're looking for. So you have to build your functional that really reflects your needs. Okay? This functional has the right players in it, because I know that I want something that is frame invariant. I wanted something that's not going to change if I just have arbitrary choice of the reference frame. Okay, so then you pick the right tensors. So if here I would see the spin tensor is very frame dependent. So I would have said, hey, I don't like, so either I'm doing a mistake, or the function that I'm trying to optimize is not representing material deformation. Okay, so this has the right ingredient, rate of strain tensor, and then you build the mathematical function that describes mathematically what you want. Then you solve this problem. This is just a mathematical problem, and then you get the result. The result is the following. So in any dynamical system, okay, this could be doesn't have to be any fluid. It's just a dynamical system that it basically goes by x dot equal to f of x in t. Okay, so that's x can be in any dimension. The problem is that then it's a little bit more complicated when you go in higher dimensions, because it's not going to be a curve, but it's going to be surfaces or hypersurfaces, but philosophy is the same. So if you are in any dynamical system and you want to ask what are the instantaneously most attracting curve at a particular time, they are the extremizers of the problem we discussed before. They are computable. This is a result of what you can get from the irrational problem. They are computable from the Eulerian rate of strain tensor, symmetric part of the velocity gradient. They are tangent to the dominant eigenvector of the rate of strain tensor. So you compute the rate of strain tensor everywhere, like you did it for Cauchy-Green. Now it's another tensor, it's symmetric, similarly, so you can use the same code. And then you compute the eigenvector E2, and then what you do, so this eigenvector now is a director field, is not a vector field, but you can still integrate director fields. Okay, you have to do some corrections because the vector field, like the velocity, tells you when you start here, it tells you where to go. With the director field, you can go either in this direction or in this direction plus pi. It's fine. You can do a little bit of correction and then still integrate director fields. This is how people compute nematic texture in liquid crystals, right? So you just integrate the nematic director back and forth. So you basically integrate this director field in the direction for the director field specified by the largest eigenvalue of the rate of strain. And where do you start your integration? At the smallest, the minima of the smallest eigenvalue of the rate of strain. So let me give you a picture here, and then we're gonna go with the examples that we have later. So basically, the results of this calculus of variation exercise, which is the optimizers that we're looking for, they are as follows, basically. This is the ocean, okay, and let's say for a particular time t, this is longitude and latitude. Here there is a velocity field. Then you compute from this velocity field the rate of strain tensor, which is dv transpose plus dv divided by 2. And then here you just compute the eigenvalues, like we call it S1, smaller eigenvalue, S2 is the largest eigenvalue, E1 is the largest eigenvector, the smallest eigenvector field, E2 is the largest eigenvector field. So we are saying, look at S1. So S1 is going to be a surface, right? Like we did it for the FTD. So let's say that S1, let's say is going to look something like this, and then whatever, right? So, okay, so this is S1. This is the value of S1 as a function of x and t, this particular x and t. So you say, yeah, look for minimum of S1, this is a minimum of S1. This marks a very important point in the fluid. We are going to understand why. And then on this domain, which like you can do it with Cauchy-Green, there is going to be another vector direction field, which is the E2 field. This would be the largest eigenvector field of the rate of strain. And this is saying that these optimizers are basically trajectories of this eigenvector field that pass through this point. Actually, they start through this point. So this is going to be one of these curves, gamma, that we were looking for, that are the most attracting curves for a very short time. Okay? That's basically what we have. Okay, now let's do an exercise. So this is basically an oceanic flow that is computed or reconstructed from altimetry. It's called basically, I think, quasi-geostrophic flow from real altimetry data. And now I ask you, this flow is slightly time dependent. And I'm going to play the video. And now I ask you, if someone gives you this distribution of streamlines, and I ask you, where are the regions where you're going to have the largest stretching of material, if you put a bunch of ducts or whatever you want, colorant, and forget about diffusion, where are the regions in this streamline field that will stretch the most? Okay? What would you answer?
Maximum eigenvector.
Sorry?
Maximum eigenvector
Of what?
of the
Oh, the rate of strain, you're saying, yeah. But okay, fine, but the eigenvectors is everywhere. Where would you, I mean, the eigenvector is a field everywhere. Now you have to tell me where. Eigenvector at most can tell you in which direction. But where should you go if you have to bet? Where would you say that there is going to be the highest chance of having large stretching?
Between two vortices, like the region.
You can start going with this intuition, and actually I'll tell you that if you go and look at the books, they would tell you, look, you should really go here, because this is where the streamlines change topology. So that's really, it's basically, this is called saddle point of the velocity field. So here the velocity field is 0, and is hyperbolic. That means that there is going to have direction that stretches, a direction that compresses. Also, this is also incompressible. So it must be that if one direction stretches, the other one compresses. So then your claim would be that these points between vortices, if you think of vortices as closed streamlines, these points are the ones where you should have largest stretching. Now, there are several problems with that. This claim is abusing results that hold for time-independent systems. So if x dot is equal to v of x and not v of x and t, and you wait for t going to infinity, your answer is correct. And in fact, those are the stable and the unstable manifold for the fixed points. However, as soon as you have a time-dependent system, and you want to ask, even if it's time independent, and you want to ask what happens for t going to 0, these answers are not the right answer. Okay? Third, these points, the fixed points of the velocity field are frame dependent. That means basically that if you do this assessment by an helicopter or by a boat that is moving or the tower station on board, you get 3 different results and you don't even know how to connect them. Okay? So let's do that. So this is basically what would you get for asymptotic methods, and this is instead what this technique is telling you. This is telling you, look, you should go to these different places, the green ones. The asymptotic ones should tell you that instead go to these 3 different places. And all these are frame invariant, the green ones, frame independent. So now what I'm going to do, I compute this at time t, and I'm just going to play a movie so that you see in the next, I don't know, whatever time scale, I don't remember what time scale, how these things will deform as a test. But this information have been computed just using one snapshot of the velocity field, like the streamline. But then if you want to say, either you say, hey, these are the most attracting, you trust me, or you have to say, hey, show me how they attract, right? So I'm going to just use a little bit of data in the future to visualize and prove this thing. If you do that, this is what happens. Okay, so basically, this asymptotic saddle point stretches because there was an objective saddle point. This is what we define, objective saddle point. This stretches also because there is an objective saddle point. Here, this guy barely stretches, and in fact, there is not an objective saddle point. Okay, these traps, basically. Here, you can have huge stretching on a region, basically, that is actually moving. There is no saddle point. And actually, this is a very beautiful exercise example, right? So this guy can move, but still induce a significant stretching. While these guys, even if you have basically a time-dependent velocity field, you can try to do this exercise and say, okay, let me actually, at T1, I'm going to look for the points such that f of x at T1 equal to 0, the x star. And you're going to get the fixed point at T1. Okay, then you do this at T2, etc. You're going to look for basically fixed points of the velocity fields. But these points, the problem is that they are basically anchored. They don't move. They're also frame dependent. Instead, you can have significant stretching also in regions that move. Okay, so why should they be still? This is just what we were expecting in steady dynamical system, but it's not true, because now you say, hey, I told you what I want. I want the curve that attract the most. I don't want to impose that they have to be still, right? You can put this in as an additional constraint if that's what you need, but in general, they can move. Okay, so now think about it. If you would do a search using classical methods, yeah, this would have a very strong consequences, because you would be missing regions where most likely things would get attracted. Okay, so is this clear? Okay.
Actually, I still did not understand why there are some reason which are not in between the vortex, but stretching is more. For example,
yeah, because I mean the fact that you think you are between the vortex is coming from some very specific observation. But I can have vortices and I can have no stretching region in between. I can construct an example that is like that, and you don't know what happens in the ocean. I'll give you an example. Think about this. So let's say that you are in a channel, and here you go fast, here you go slow. Now think really about putting some tracers here. What happens? So let's say you put them here, put them here, here. In a little bit, they moved. They all move. But they will squeeze this blurb of thing from this configuration, squeezes here, because it's like when you go, you go out, someone is running faster than you, you go slow, you're clogging the lane, and you're gonna have a bump of density of people near you in the back, right? So there is no vortex here, but I can still have strong accumulation. There is no fixed point. Okay, now think about it. I can, the ocean is very complicated. So a combination of vortices, this phenomena, and many other that can generate very exotic distribution of attraction, etc. But you don't have to think or care about it. Forget a little bit the intuition. Do this, and you're gonna get the answer. So you know that there could be many different combinations of. Maybe they are also very counterintuitive. Okay. Okay. So what we did. So this was basically, actually many years ago now, unfortunately. So then what we did, we said, so there was a group at MIT that the group of Professor Tom Peacock, he basically wrote a big grant on using recent methods to mathematical methods to help hazard response, and then they said, okay, let's test this with in real experiments, and this is the field experiments that we did. So we went. Martha's Vineyard is just in the east coast of Boston, so just outside Boston, a couple of hours, even less, just really by the coast. And so the Woods Hole Institute of Oceanography is basically a very famous institute of oceanography that has a lot of instrumentation in this area, close to Martha's Vineyard. Specifically, okay, they have boats and all these tools, but specifically they have a region on the ocean here where they have a lot of towers here that can measure the ocean surface, and then with these measurements and some algorithm, they can actually reconstruct the velocity field in this region. So we said, as a first step, let's see if we have a good quality velocity field, if we can predict where things go. Okay, so what we did, we used this basically sensed surface velocity field. We computed these traps, and then we deployed the drifter and mannequins with boats, and we said, okay, do they go to traps, yes or no, how long does it take, and etc., right? Okay, so this is step number one. And step number two, we said, let's do something more challenging. Let's actually now use a model-based velocity, which is more typical of what happens in the Coast Guard, because when there is basically a search and rescue, it's very unlikely that you're gonna get available ocean surface velocity that is measured. Well, it's the Titan, it's in the middle of nowhere. How do you know? It's actually also at depth. Even there is no way you can measure anything. So you really have to rely on model-based velocities, and this is more challenging because, of course, this means basically that there are a lot of more uncertainties. Okay. So this is the team. So this was my first paper with this. Okay, so the traps, so this thing, I did it with George. This also was done with George. This is when I was finishing up my PhD. So George and I did the theory part. Irina was at WUI, the Woodsole Institute of Oceanography, is very famous, expert in, in oceanography. She had a lot of data on drifters. Anthony did all the high-frequency radar measurements. Shane Ross did provide the mannequins with the tracks. Pierre did all the modeling of the ocean modeling, so the PDs for simulating ocean modeling. Art Allen was the command, was basically the lead responsible of U.S. Coast Guard for search and rescue, and Tom Peacock was leading all the experiments, and he wrote this huge grant. Okay, so that's basically what we did. So for the first trial, they already had basically a very good data set of drifters deployed in this area and the velocity. So we said, okay, the data is already there. Let's use the velocity. Let's use the trajectory of the drifter. Let's see if they really go where you expect. So distribution of drifters, very spread out. This is the streamline. So you think about now the streamline. There is no vortices here. So you say, okay, actually I would expect that everything is just flowing and nothing is accumulating. Instead, 2 hours after this spread out distribution, you can compute these traps. This S1 is exactly this field. So the more negative it is, the more attracting it is. And these regions are exactly this eigenvector of the rate of strain, the red ones. So you can see that there is going to be traps that are the most attracting. The more blue it is, the more attracting it is. Okay, so this is -10, here is -25. This is real data, and this is the motion of the drifters. So they start clustering in this very spread out distribution. Again, there is no sign of this accumulation on the streamline, because this is actually, it's happening something like this here. It's precisely this that is happening here, which is very hard to spot from looking at the velocity, the streamlines. And then after 3 hours, you get even a stronger alignment, because basically this is getting stronger, more homogeneously stronger. This was a localized stronger, maybe it was the one that generated this huge kick, and then this was becoming, a strong attractor more broadly. And this is after 3 hours, okay? And then if you look at the divergence, this is not really driven by divergence. I have a slide at the end, because this is also something that the other people asked yesterday. And you can have traps, accumulation regions also where the divergence is positive or close to 0. Okay, so you cannot really get this from the planar divergence. I have a slide at the end. Okay, so this was interesting, and we said, okay, this is cool. At least it's going in the good direction that traps can predict the motion of floating objects. Remember that traps are just based on fluids, while these floating objects are not really following the fluid particles. But for very short time, they're very close, because the correction hopefully is small. If it's not small, there is no way you can sort of predict them, unless you tell me what they're doing or what's their properties, etc. Okay, so that's basically, okay, the video, how they basically cluster. Oh, it's just what I showed you now. So then the second time we said, okay, now let's instead use modeled velocity field, which is not, there is no available data on the ice surface velocity. It's from the model of Pierre Lermoisat at MIT. What we did, we said, okay, this is the situation with the traps. So this is basically the S2 field, S1 field, what I just told you. Eye attraction is in blue. And then we had, I don't remember, 1, 2, 3, 4, 5, 6, 7, we had 8 drifter and 4 mannequins to deploy with the GPS. So Pierre gave me the model of the model velocity. I computed the traps in this region of the ocean. And then we said, let's actually go out with boats and deploy this bunch of drifters at 10:15 and mannequins and see where they go. The idea was that they should go to these red structures, the traps, right? So this is a drifter, this is a mannequin, and this is basically how they look when they are in water, basically. This guy is basically in the water, this also guy is in the water. Well, after 1 hour, this is basically how they went. So after 1 hour, they already went so quickly to the traps. I mean, of course, there is some variability. This guy is still sitting here. Didn't really move much after 1 hour. I mean, 1 hour of ocean time scale. Ocean time scale, 1 hour is nothing. Still, these guys were able to make it to the trap pretty quickly. After 2 hours, even a stronger distribution of these objects to the traps. Okay, this guy is making his way there. Of course, I mean, this is not, there is a lot of, uncertainties and, things that we're not accounting for, but, in 2 hours, we were really able to predict where things were going. And of course, the traps are evolving. So as soon as I have a new batch of velocity, I can predict and update this S1 field, the E2 fields, and I'll recompute the traps. Okay. So this was reassuring because also when we have model-based traps, we can predict the motion of, floating objects. Now, this is something that I don't remember who asked this question yesterday. I just pull up these slides. So what we did here to understand sensitivity to noise. So, whoever was in boat that started at A and B, they had both to deploy a drifter and a mannequin and a drifter, mannequin and a drifter. That means basically that these objects, they started at the same position, and then they underwent slightly different dynamical systems because one guy is a drifter, one guy is a mannequin. The magenta one is a fluid particle that integrated with the model. Okay? And the interesting thing that despite they actually separate even within 1 hour, these are basically already separated, but the separation is basically collapsing onto the traps. It's a very interesting thing that says, these traps are really capturing the robustness of, the noise or the underlying process. So it doesn't really matter what kind of object is floating unless it's basically a whale that, flies in the water. But otherwise, there are basically very little distinction. I just go to the trap, okay? So different trajectory, same trap. So then if you want to understand this, you can actually do a little calculation and say, okay, this is my Ito process. So I'm going to have a deterministic velocity and some noise, some stochastic part where this is the diffusivity, so the structure of the noise. And then what I can compute is the rate of strain tensor of this uncertain process. If you do the calculation, actually you can see that the rate of strain tensor of a Langevin equation is going to be equal to the rate of strain tensor of the deterministic velocity field plus a rate of strain that comes from the noise. Okay, and this disturbance or noise rate of strain is nothing else than the diffusion tensor of your noise. You differentiate it with respect to x1 plus the diffusion tensor differentiated with respect to x2, and you take the symmetric part. If you do the calculation, this is what you get.
D is diffusion, right? So
diffusion is not diffusion. It's just to model random walks. There is nothing is diffusing. It's just that there is a stochastic differential equation. Yeah.
But how do you define this tensor? How will you in general? So you can measure noise level and then from there you get.
No. You just have a differential equation. This is a vector. V plus D times dW is a vector. Now think of this as a vector field.
No, that part is, I'm just thinking about the diffusion, because usually you consider that diffusion is going to be uniform. We
are going to get there. Let's see what's going to happen. It's even more cool because, okay, yeah, this you can, in experiments you can measure if there is a structure or to this noise, etc. But very good point. So let's say this is the way you compute it, but typically D is uniform in space. Because if you know the structure of this noise, then you build it in the model rather than leave it in the stochastic part. So this is interesting because it says that if D is just a function of time, eventually, actually it's not even a function of time, usually you say it's constant, but okay, also if it's a function of time, this guy, so the disturbance part or the random part of this rate of strain tensor is 0. So that basically means that the coherent structures, the traps, will be completely unaffected by the noise. And in fact, this is a sort of a very elegant explanation of what you observe with real experiments, right? Okay, so this is cool because it's saying, oh, you know what? Unless you have a very particular structured noise, that it would be hard to know, and also I think very likely hard to realize that there is going to be preferential direction in regions of the ocean on the noise, not on the velocity. So if that's the case, these are very robust predictors. Instead, now if you go back to the Lyapunov exponent, if I would do a Lagrangian prediction of I start basically at the initial condition, the growth over some particular time t will be proportional to the largest Lyapunov exponent times square root of t. So Lagrangian predictions will immediately start accumulating noise proportionally to the largest Lyapunov exponent, which tells you how much separation can you achieve times square root of t. These guys are remaining completely unaffected. Okay. So this is basically a way to say that these traps are robust to uncertainties. Okay. This is that's a little other consideration that you can have a very beneficial very big benefits from considering these instantaneous coherent structures compared to trajectory based one when you want to address this type of problems. And so basically the summary is that you can have fluid-based traps, basically are short-term attractors of general floating objects. They are 1D curves, so they're really optimal to search. They are robust to uncertainties, very quick to compute. You don't have to compute trajectories, etc. You just have you can actually build them into the ocean models that are available, so that the coaster doesn't have to do anything, just computes, and they have basically these maps of traps. Actually, we are developing a pipeline or a website in which you basically plug in your coordinates, and it's going to tell you immediately where these traps are, depending on if you want to do oil spill, plastic collection, etc. And they are actually hidden to velocity field plots. So this is to say that you can look at vortices, etc. But I mean, these considerations were not really designed. When you look at vortices, etc., nobody's telling you where do things go. Okay, so when you have basically vertical flows, etc. Instead, here the reason it works is that because we design it to be that way. So we said, okay, we asked where are the curves that are the most attracting in this flow, and then we just did the mathematical exercise. And this is now adopted by the Coast Guard as one of their techniques for doing search and rescue. Another application that we did is basically associated with oil spill. So we also showed that knowing the presence of these traps would have predicted, about a week earlier where to go and bound the oil spill containment, the Gulf of Mexico. This is basically a book with NOAA and other collaborators. Rodrigo Duran is an oceanographer in Miami. And there is also a nonprofit company in the Netherlands. It's called the Ocean Cleanup. They're trying to clean up ocean plastics, and they are using traps to basically they go with these interceptors, and they want to basically understand where these traps are depending on ocean velocities, etc. And they're basically using this technique to see where to go and find the regions of highest likelihood of finding these traps. So this is basically the full reference, the team. That was a very beautiful joint effort. That was very casual. This really came up as a spontaneous, collaboration. And I just want to point out a couple of things. I have maybe 2 slides, this and another one. The first thing was something that one of you asked, I think Sahil asked about, divergence, attraction, repulsion, and this is basically the same question that the reviewer asked when we were submitting this paper. The formation of a fluid patch, there are 2 contributions. We already saw it yesterday, right? So it's isotropic one, this could grow, or could shear, preserving the volume, okay? And the total is just, what you observe is a combination of the 2. Now you can have basically attraction in a region of positive divergence, because basically, look at this. Basically, this guy is going to increase volume overall, but he's going to squeeze in this direction way more than stretching in this other direction. So although the phase space volume is increasing, I can still perceive attraction in this direction. Okay, so basically, the divergence is not the only thing you have to look at, unless you are looking at asymptotic attractors in the classical sense of dynamical system, where you wait for infinite time and you really shrink phase space. Okay, but this is basically short time. So even finite time, this is important. In finite time is the same. Attraction in a region of 0 divergence, that's very standard. I attract here, repel here, but the area of the patch is the same of the area of the deformed ellipsoid. And I can also have actually repulsion in a region of negative divergence for the same reason. So basically I can start with this blob, I can shrink its area, the elongated object, but then I can basically have that the repulsion or the stretching is much higher than the compression. So basically, this is something that can make sense of something that could be maybe possibly counterintuitive. Okay, so the divergence is not going to tell you necessarily where there is attraction or repulsion. Okay, so this is one. The other thing I decided to put in the slides is something that I think some of you are also already facing, which is that whenever you have data on a finite size data set, so let's say that this was the data on south of Martha's Vineyard, where I had the high frequency radar velocity, or let's say someone does an experiment. This is what you have. The data is you have data, the velocity field data inside this domain, because outside there is no microscope. Now, one thing that you have to be careful is that if the velocity field is outward flowing, means that it's going out, okay, then there is a problem, because you start here and then by a certain time this trajectory has left the domain. So from that point on, there is no way you can tell me what Lagrangian process has happened here, because you don't have more information. Okay, and if you, in this particular oceanic example, you can see basically that the more you push the integration time, the least information you have available, because most of the trajectory are likely leaving your domain. Okay, so this is an important thing when you have real data. There is usually a finite size domain in which you have data, and if you want to start cranking the integration time, you're gonna not be able to address things. But the Eulerian methods are always there, because you have velocity here, you're gonna get coverage forever. This is also something that you have to consider. And in fact, if you remember the slides on the chick, there were basically regions that became white progressively. A larger white region on this domain is because these cells were actually leaving, so I didn't know how to, the repeller number 1 was actually very eroded, from the experimental data for this reason, okay? Because cells are leaving, so unfortunately you cannot really address this point. So another thing you can do is define the notion of instantaneous Lyapunov exponent. So if you, instead of expanding Cauchy-Green, you expand the finite time Lyapunov exponent, which I'm doing here, you actually recover the largest eigenvalue of the rate of strain. So the instantaneous repellers, you can read them from the largest eigenvalue of the rate of strain. Okay, a diagnostic to understand short-time attractors, you can just look at the smallest eigenvalue of the rate of strain, which is S1. If you just don't want to be so precise and tell you in which direction I want to pretend normal, attraction. So if you're not caring about enforcing normal attraction, but you can also accept, shear type attraction, okay, then you can just look at S1 instead of basically looking at also the eigenvectors. And so now you can have basically short-time attractors and short-time repellers. These are Eulerian, so you can also start doing optimal control. So because controlling Lagrangian attractors and repellers is very complicated, because basically you have the velocity field that you don't know, then there are functional of the velocity, which is the trajectory, and then the Lyapunov exponent, a very nonlinear function of the trajectory. So doing optimal control for attractors and repellers, for instance, could be, I don't know, how should I design the distribution of myosin such that I create an attractor? Okay, that's very hard to do mathematically, but then you can start, at least we started asking, can I create a short-time attractor? And the answer is yes, we can, and you can actually use optimal control and active nematics, in which, in this case, we use the same equation for the chick development that I showed in the morning, and I said now myosin is not a field that evolves by itself, but is my control variable, and I asked, how can I create the desired distribution of short-time attractors or repellers tuning myosin? Because, generalizing a little bit development, eventually development can be thought as, a set of attractors and repellers, in which basically the attractors make sure that the right cells go to the right place, and repellers make sure that distinct cells, they separate from each other. So eventually you say, okay, maybe the embryo is trying to optimize attractors and repeller geometry, and then, this is a first attempt in which basically we controlled M to achieve a particular configuration attractors and short-time attractors and repellers. And I think that's all I have. And if you have more questions, or if you have questions, I would be very happy to take them. Yeah.
Thanks.
Question?
Yeah,
Actually, I just want to understand in the ocean model.
yeah,
So where there is a short time attractor.
yeah.
So since we know that the attractor won't be constant for longer time, they are very short in time.
Yeah.
So how one can track it within that short time because lots of motion is going on.
Yeah, I mean, no. You can. What do you mean? You can track it. You know, this is, for instance. So this is real. You know, these forget models. This is real data. So you see, this attractor pops up, and then I track it for 1 hour to the next hour. These are all structurally stable features. They are very robust. So they will not disappear in a split second. They can deform a little bit, move a little bit, but they will not disappear. Okay? So they're always there. Then you can also ask how strong is this attractor? What's their robustness? You can see if I perturb time a little bit with Poincare section arguments, you can actually, or implicit function theorem, actually you can understand, or actually classify all the present attractors and say short-time attractors and say this guy is going to be most robust than the other guy. So this could be also an additional information you can use to say, okay, I'm going to chase this guy instead of the other guy. Yeah, now, for instance, an interesting question could be, similar to what other people asked yesterday. You say, okay, I already know the equations that govern ocean surface dynamic, and I ask you, what forces generate these objects? This is also something we're trying to investigate, right? Because there are a lot of forces on the force balance on Navier-Stokes, but then can you actually say that, contribution of a couple of forces when they are in a particular alignment with each other guarantee the presence of attractors? So you can start asking these type of questions on the cause of this, and then maybe say, okay, can I design a flow that has these particular attractors? Yeah. Yeah, other questions? Okay.
So just to get it, so suppose if we have an Eulerian field, you can calculate the strain rate tensor. From there, you calculate the eigenvalues and eigenvector for what is the minima of S1 and where the largest eigenvalue is intersecting, and that is going to be the point where attract.
Yeah, that's it. So that's it. Yeah.
That's what we have.
Yeah, actually, guys, in this paper, on my website, in the publication tab, there is a code there is a code for commuting traps. So you can basically use it. You plug in the velocity you want, and it's already there. But yeah, that's the result. Yeah. Yeah. Yeah.
And usually, so of course it is going to be dependent on if the dynamics is really fast, so attractor will be moving around in this.
Yeah, we're moving around. Yeah.
Do a correlation and try to see the lifetime of these stuff.
Yeah. I mean, the ocean surface dynamic here, it is fast.
Yeah.
Actually, especially here because there is a channel. So this is very fast because usually when you go, what I understand is that basically whenever you are near coastal region, the strength of the ocean currents are much faster because there's boundary layers, some of this kind of stuff. But in the middle of the ocean, it's way more calm. And these experiments were done close to the coast because it's easier to reach. Yeah.
Thanks.
Okay.
Okay. Thanks.
Of course. Yeah.
So in the second half, what will resume from where we left. So what we do first try where we left, because unless you figure that out, we cannot move forward. Okay? So the aim is that spend some time, try to use your Rollman flow again, use the data, and try to see if you can find the finite time or the exponent or not. That you should definitely try to do. And once you manage to do that, then we will. Then you have to write down the equation for the inertial heavy particles and try to see whether they are going to get accumulated in the strain dominated region or not. And if that happens, then you have to check what is happening with FTL. Okay, that is one thing. And then the third aspect would be so. Actually, first we wanted to give you real experimental data, but data is very noisy and it will be we realize that it is too challenging task to handle. So it's better you do something which is much more smooth and much more controllable.
It's exactly the same. Once you have the code for a velocity field, then you can just use it for any other code.
Yes.
Yeah.
It's better to handle the flows that we understand very well. So so for tomorrow, what you will be doing, you will be taking the same velocity field that you have already done. You have looked at the vorticity field, right? So that flow. You take that flow and try to calculate the short time delay upon exponents. Like use the Eulerian field. You find where is the minima of S1 and which the eigenvector corresponding to largest eigenvalue where it is going to intersect, and that's going to be your attractor. Okay.
Yeah, okay, you can also guys, I mean, it's good to plot the eigenvector field.
Important plot, visualize, get a feel for it first.
Yeah.
Then you
don't compute the trajectories of the eigenvector field, because that's a little bit a delicate thing. Or you can go to my website and then use the code that is already there. But even if you just plot the S1, it's already a good.
that will say what is the point, and then
Yeah, exactly.
you need to find the direction. So
Yeah.
So that's the plan. So today you will still be dealing with the agent based Lagrangian data. We expect that you get a good control on FTL finite time Biacono experiment, and then we will not be covering that tomorrow. So tomorrow it's a new problem. Okay. So we hope that you manage to do it. And please, if you're not able to fix it, note down your questions. We'll be around in of course PS210, and tomorrow also will be available. And for Eulerian, that's all.
Yeah.
Okay. Okay. Thank you, everyone. So we'll disperse for lunch, and then we'll meet at 2:30